Hi, everyone. We're just letting everyone have a chance to join, and then we'll get started in about a minute. Okay. Looks like it's 9 o'clock. Okay. People will continue to kind of trickle in as we go along. So I want to welcome everyone today to our EGI spring webinar. We have Dr. Kristie McLin with us. She is Director of Research and Science here at EGI, and she's Principal Investigator of Utah Forge. And she's going to be presenting today. We will have a Q&A towards the end of the webinar. And if you want to drop a question in the chat box, you can do that, or you can use the raised hand function and we'll get to you that way. So the webinar should last about an hour or less. And so I am going to introduce Dr. Kristie McLin here, and I will hand it over to you now.
All right, thank you very much. Appreciate everyone calling in. And yes, feel free to ask questions throughout the webinar. Happy to answer anything as it comes up. Today I'm going to present an update of activities and plans at Utah Forge on behalf of the Forge team. So a little bit of history of Utah Forge. In 2014, the DOE announced the FORGE initiative, and FORGE stands for Frontier Observatory for Research in Geothermal Energy. And at the time, the DOE had a goal to make enhanced geothermal systems commercial through demonstration. And so in 2015 to 2016, 4 teams proposed 5 sites, mainly reviewing established data that was mostly derived in the 1970s during energy crisis and from oil industry exploration, and continued research of these sites that were characterized pretty extremely well back in that time. And then the DOE down selected to 2 sites, and each site was funded to drill a demonstration well to confirm the subsurface conditions that they thought were most suitable for an enhanced geothermal demonstration. And in 2018, Utah was awarded the Forge contract, and construction of the field laboratory began. We've had a significant external research and development program, and we've been able to demonstrate connection between injection and production wells, which was the main goal of the project. In this current phase, we'll be conducting extended circulation testing, drilling another well, stimulating the wells, and then conducting longer-term flow tests and evaluating temperature decline. One of the great things about the Utah Forge project is that everything, all the data is available publicly without any cost. And we've had over 133 terabytes of data loaded to GDR since project inception, and significantly more to come with our upcoming activities. So if you'd like to access it, go ahead and use those links or QR code. If you have trouble finding something, feel free to reach out. We're happy to help you find what you're looking for. Now, a little bit about the geology of the site. The geology of the reservoir is that it's predominantly granitoid and some metamorphic rocks. There are rhyolites up in the Mineral Mountains to the east that are about 750,000 years old, related to the current heat source of the Forge Reservoir. Basement sediments lie unconformably on top of that granite, and the Opal Mound Fault that you see separates the Utah Forge site, which is the enhanced geothermal demonstration site, from the existing hydrothermal site. You can see on the map there's a little dot called, or a square called Blendell. That is a current hydrothermal power plant. Reservoir rocks are high strength and very abrasive, granitoid and metamorphic rocks, as I mentioned before. Very low inherent permeabilities of 30 to 80 microdarcies. And we have not found a water phase inherent in the reservoir. So we were able to find the hot dry rock that the Forge initiative was looking for. The wells were pretty extensively characterized with geophysical logs and FMI being one of them. And you can see here that there is a comparison of the FMI fractures to the core fractures. And all of this information, and then some information during hydraulic fracturing, has been added to a DFN, that discrete fracture network, that you can access in the GDR. And then you can see how those fractures are oriented. You can manipulate and view these images without needing any specialized software. So as I mentioned before, the focus of the Forge project has been on data generation and sharing. So we have many seismic monitoring wells, and these wells are located surrounding our injection and production wells. The initial well that was drilled was the pilot well down in the south, the 5832. And we have monitoring wells as deep as about 9,500 feet measured depth. And we found that seismic monitoring can be accomplished with shallower wells, which will save cost on commercial operations. However, we are getting a very high degree of accuracy in locating seismic events based on our configuration. A bit of a timeline on the progress of the project. As I mentioned before, in the 2014 to 2016 timeframe, data was being collected, assembled, seismic monitoring began, and geophysical surveys were conducted. The pilot well 5832 was drilled in 2017, and a DFIT was completed in 2018. Additional monitoring wells were drilled, and a small stimulation was completed at the bottom of 5832 in 2019. In 2020, the injection well was drilled, and that's the 16A 7832. A couple more monitoring wells that were much deeper were drilled in 2021, and then 3 stages were stimulated in 16A in 2022. Now, with the seismic monitoring and being able to see where we thought those fractures went, the team was able to determine where to place the production well 16B 7832, and it is placed above the injection well and drilled through the fractures that were generated in the 16A fracture. So a short circulation test was done to confirm that there was connectivity between the injection and the producer well. And this was a big step forward in enhanced geothermal system design. And the groundwater well was also drilled in that year because we needed non-potable source of water to conduct longer term circulation tests between these 2 wells, and additional stimulation. 16A and 16B were then further stimulated, and a long-term circulation test was conducted in 2024. And that was there was a 9-hour circulation test, and then a 30-day circulation test that was conducted in that year. In 2025, we had some well cleanouts and plugged to 5832, and then Texas Tech and California State Long Beach came in to have some testing with the R&D program that I mentioned earlier. And we have a fiber optic cable in coil tubing as a result of those tests. So initially, the stimulation design is shown here, where stage 1, 2, and 3, as I mentioned, were the initial stages that were fractured prior to the 16B well being drilled. And then you can see stage 4, 5, 6, 7, 8, 9, and 10. The first stages were refract at the time that the stages 4 through 10 were also completed. And then small fracs on the 16B to ensure connectivity were completed. Fiber optic cables were installed and in 16B and proved to be very important and useful information in determining where those fractures were connecting with the 16B well that were fracked in 16A. And the objectives of the test were commercial rates of production, understanding whether proppants were needed or not, and we think they are. Bridge plugs were tested and some failed. Number of clusters per stage were tested, different treating fluids, some slick water and some crosslink. And then application of fiber optic cables, as I mentioned, proved very important with seismic, strain, and temperature data. And the role of natural fractures in understanding how these rocks actually broke in stimulation made a big impact. We also used two different types of tracers. The first type of tracer is a solid tracer, and this tracer has high temperature stability, very good detection, unique distinctive tracers that can be added to each of the frac stages. And then we sampled during flowback from 16A and from 16B during circulation testing. These tracers are inert, non-hazardous, and non-radioactive. The other type of tracer that we used is a water-soluble chemical tracer, temperature stability well above the temperatures we're working in, detection limits in the parts per trillion, and a unique tracer was added to each of the frac stages in 16A. And then we sampled during flowback from 16A and from 16B during circulation. These are also inert, non-hazardous, and non-radioactive. For the seismic monitoring program, we had geophones. We found that placing geophones at about 150 degrees C is optimal, where they last, the duration of our activities and collect meaningful data at a depth that is closer to where the hydraulic stimulation is taking place. We also have surface nodal arrays, and we just got finished installing our latest array for our upcoming circulation test. So this is probably one of the most important slides I'll show during the presentation, so I'm going to spend a bit more time on it. As I mentioned, 16A, which is the injection well, was drilled first and then stimulated, and then 16B was drilled through the fractures. And the B well is above the A well. It was placed there because it was thought that that would be best for buoyancy and convection. Now, the location of the stages you can see on the diagram as the dots. And we've made a stylized image essentially showing the corridors of those different stages based on the fiber optic data that I mentioned in 16B. We also did production logging during the circulation testing, and you can see that dashed line is the maximum depth we could get that tool to. And then on the right, you can see the microseismic events detected during stimulation for stages 4 through 10. So what you see is that initially in stages, the refract stage 3 and 4 and 5, the frac hits were almost directly above the 16A well in the 16B well. Same for stages 6A and 6B. And you can see the corridor for stage 7 start to slightly lean over heelward. Now, we had a lot of trouble getting proppant in on stages 6 and 7. And so that definitely impacted how much flow we were getting from those stages. You can see that about 36% of the flow was coming from below that maximum production log depth. And then, as you see for corridor stage 8, there were the first frac hits from that stage were all the way heelward and then started to move back down the well as the stage progressed. And that was a very interesting finding that indicated to us that we were having a significant impact of geology on the way these rocks were breaking and then the predominant direction that we were getting those frac hits from. And you can see in the microseismic that we have some planar features that are starting to show up in the microseismic at the same time. And then the corridors for stages 9 and 10 follow along, and frac hits were seen uphole as well. And so you can see that flow is dominated by the heel, essentially, both based on geology and probably what we expect in the upcoming circulation test is some heel bias due to hydraulics as well. This is very important for framing what we think is going to happen in our upcoming circulation test, and significant simulation has been done based on this work to try to understand when we'll see that thermal breakthrough as a result of understanding where all of these fractures are and where the flow is predominantly going in these stages. Geochemistry is another tool that has given us a significant amount of information and is very inexpensive. So if there's anything you want to do on a commercial scale and save some money, geochemistry would be one of the things I would tell you to choose. Interestingly enough, as I mentioned, we haven't found water in our natural fractures in our reservoir. That being said, we do think there was water there at some point because we have fractures that we've characterized in the core that are filled with highly soluble minerals, halite, which is sodium chloride, your normal table salt being one of them. And those minerals are there as a result of probably water dehydrating. And you can see then as we start to circulate fluid through the system, we're picking up a lot of those minerals, dissolving them in and producing them. So we're seeing changes over time in our produced water that are different than what we've injected, and that we expect to, as we dissolve those soluble salts out, we expect to see less of that because we expect also the water to be connecting and contacting that same surface area with progressive circulation. So we'll have fewer of those minerals left to dissolve out and return to the surface. We also are seeing some scale minerals depositing. We've recovered calcite and magnetite deposited on pipe. And the calcite is from the fluids that we're injecting being saturated in calcite at near surface conditions. And calcite has a retrograde solubility, so it's going to come out as you heat water. We are treating with scale inhibitors. And another thing that we think is going to help us out is that although we're not seeing water in our natural fractures, we're seeing a CO2 rich discharge, which tells us that we're connected more deeply to a deeper source of CO2. We think it's magmatic as a result of our stable isotope testing. And that CO2 may also be why we see that dehydration of the previous fluid that was in those fractures. That phenomenon is seen in CO2 sequestration, for example, and so we think that has a big impact. However, a certain amount of CO2 held in solution, maintaining pressures will reduce the pH and will also improve our scaling without additional chemical treatment needed. However, we are going to be adding those additional scale inhibitors, corrosion inhibitors, and possibly oxygen scavengers in our upcoming circulation tests. So just to highlight the results of the previous circulation test response, we were able to improve efficiency over time with the extended circulation of 30 days. And you can see that plot on the lower right, showing that over time we were recovering more of the fluid that we were injecting. And that's good news, but 90% fluid recovery is still a challenge for the industry. So we want to test methods for improving that. Potentially one of them in our upcoming test would be to install an ESP in one of our production wells. You can see the produced fluid temperature leveled out was relatively stable at about 188 degrees C. And you could see that the mass flow rate was pretty stable over time. So a bit of information about the pressure. It's very interesting that once circulation had ceased, we were able to see pressure fall off, wellhead pressure fall off, and both the A and B fell off at the same rate, again, indicating hydraulic connectivity. Interestingly enough, our monitoring well 5832 also fell off. That one is one of our deeper monitoring wells, and that's the one the CO2 was coming out of. So we think we are connected to that monitoring well via hydraulic fracturing, and so that well has been plugged. As I mentioned, there have been a significant amount of numerical simulations, and that discrete fracture network is available on GDR. And if you would like more information about it, please feel free to reach out. As I said, you don't need specialized software to see and manipulate the DFNs and see which data was used to characterize which fracture sets. And then with that data, with that extensive data and the production data, significant amounts of modeling work, both within the Forge team and the R&D team, but then also outside of the Forge project, have been published. And we believe we're going to see a significant temperature decline based on our understanding of the reservoir, based on circulation testing, based on the recent R&D projects from Texas Tech University and California State Long Beach, somewhere in the range of 4 months during our upcoming circulation test. And we've been able to evaluate geochemically what we think is going to happen from fluid rock interactions, evaluating, as I mentioned, those temperature declines, and being able to estimate what we think our conductivity of the fractures are. Now, the image that you see to the right is from a recent publication. There are more recent publications from this year's Stanford conference. Rob Pagorny and his team at Idaho National Laboratory have done some extensive work and have presented and published that recently. So to summarize some of the breakthroughs that have occurred in the industry due to the Utah Forge project, the decrease in drilling time is not to be understated because the cost of enhanced geothermal system was significantly impacted by drilling costs with bits that were used previously, which were more roller cone bits. The drilling costs were reduced by 30% utilizing new PDC bit designs applied from learnings in the oil and gas industry, and then also taking over the best practices in mechanical specific energy during drilling. And that cut drilling times by about 50% in partnership with NOV. And you can see on the right a graph showing the initial well that was drilled, the 5832, using more conventional methods, and then down to the third well, the 78B32, which had a 2,100 foot record run. And achieving commercial flow rates and temperatures on a 30-day test was also significant. Pioneering fiber optic measurement for high temperature strain and acoustic gave so much information about where the energy in our stimulation was going. And then microseismic monitoring for hazard analysis, for watching induced seismicity, and characterizing the behavior of the reservoir was very significant. New tools were developed, tested, and failed for high temperature environments, and we hope to continue developing, testing new tools for high temperature environments in our upcoming tests. Drilled, cased, and stimulated the first highly deviated geothermal well, very significant. And the demonstration that geology was important, it feels like a no-brainer maybe to geologists, but it's always difficult to put quantification of the impact of geology on the operations of the field. So working through to show how those fractures, how the natural fractures impact these systems will be very important, especially in our upcoming circulation test. And then a significant amount of effort has been spent in informing the public, the local stakeholders, national stakeholders, scientists, and regulators about geothermal energy. It's very important that this is done well because it opens doors to commercialization that wouldn't have existed without this significant investment. And I think that operators near the Forge site benefit tremendously from the groundwork that was laid by the communications team for the Utah Forge project. That being said, it is also highly important that regulators now understand what geothermal means and are up to speed on it in such a way that I was in Washington, D.C. for Geothermal Rising's Capitol Hill Day, and I don't think there was anyone I spoke to who wasn't at least background aware what geothermal was, what it meant to the US, what needed to be done still, and it has bipartisan support, which is very important. I don't think there's another energy source that is as well liked by both sides of the aisle. I see there is a question. Do I believe that pore fluid prior to development was CO2 dominated? Yes. Well, I think there was water in the fractures, in the natural fractures, but that water I think was then dehydrated by CO2. Um, I, so I think there was water, but not recently in the pore fluid. Yeah. So CO2 dominated on the EGS side. That being said, on the side where, on the other side of Opal Mound to the east, significant conductivity of water over there, which is why you have that hydrothermal system on that side. But for some reason, that Opal Mound fault seems to be serving as some kind of hydraulic barrier between, the hydrothermal system and the EGS system, where you're predominantly seeing CO2 in the fractures. And then I also think we enhanced connectivity back to that system with our hydraulic fracturing to the CO2 in the magma. Yeah, that makes sense. Would that make Forge site rather unique? That is a very interesting question. I am not sure we know that, but I do know that CO2 is quite prevalent in geothermal systems in general. The question is whether you see more exclusively CO2 versus water and other gases. I think we will definitely learn as we go with enhanced geothermal systems how many of those sites are going to look similar to a forge and how many are going to look differently. Hopefully with the new announcement, a funding opportunity from DOE and eventually awarding of those grants, we'll get more information on more systems with different geologies. And so we'll be able to answer that question as to whether Forge is rather unique in that circumstance. Yes, I believe there is a commercial company with a lease adjacent to Forge. Has there been synergies with them? Yes, I would say that there has been a significant amount of collaboration to date with the team next door, and we speak with them fairly frequently on the topic of coordinating our operations and our seismic monitoring. And so they use some of our setup for seismic monitoring. And then we also have discussions with them on various other topics. We've been able to leverage the same team essentially for chemical, uh, so that we understand what scale inhibitors, what corrosion inhibitors, and what other chemistries we might want to use. Um, just caught up with their geochemist a couple weeks ago. So we do try to work together where possible. Of course, knowing that they had an IPO recently and that made things, a little quieter for a while for obvious reasons. But we definitely do try to stay in communication with them and are always up for running additional testing for them. All right. Any other questions before I talk about our upcoming activities? Okay. Oh, can I share a little bit more about what kind of fiber optic measurements are being taken and what kind of equipment is being used? Um, at at present time, all we have is the fiber that was installed in the 16B well stopped working about a year in, so we're not getting data from that um, any longer. We now have coiled tubing installed fiber optic in the 16B well, and so we're able to get mostly temperature data from and acoustic from that, but not as much strain. We're trying to find ways of backing out strain, but we're not sure we're going to get good strain measurements on that. The kind of equipment being used, the fiber optic cable that did work for about a year was Shell actually helped to install it. And I will have to check, but I believe it was a flat pack. And I think that's the one that worked longer. There was another one installed that did not work very well. Did that answer the question? Do you have any specifics? I can send you afterward a couple of papers that cover the fiber optic testing for Forge if you'd like. And we are going to have Shell helping us again with installation of fiber optic in the upcoming well that we'll drill later this year or early next year. And that being said, if you're out there and you're in a company that wants to be involved in upcoming testing, feel free to reach out. We are always having conversations and always willing to learn from others that have a lot of experience in this space, knowing that we're all learning together in the enhanced geothermal space. So, okay, I will definitely send you those papers after this presentation. Any other questions? These are good. Thanks for sending them throughout the talk. All right, so phase 4A activities for this year. We are building a surface facility for circulation testing. Largely, it's essentially a power plant with no power generation. In our previous circulation, we took the water, we injected it, we produced it, and then we're essentially floated out and disposed at the end. What we're trying to do now is close the loop on the surface where we have the injector well produce into a system of pipe and then is cooled in cooling towers and then re-injected at a temperature around 65 degrees C. That's a little cooler than what we would expect a commercial operation to be, but since we're trying to observe thermal breakthrough, we're hoping to speed the process a little bit by injecting that cooler fluid. The reason that commercial operations tend to inject at a higher temperature is it's a balance of extraction efficiency with scaling potential, essentially. So by keeping that temperature higher, most commercial operations are avoiding having to dose as much chemical into the system to keep that scale in solution. The cooling tower is not necessarily needed if you have the cooling tower would be required for your working fluid for your ORC, not necessarily for the water if you were in an actual operation. The circulation test will be about 4 months, and that 4 months is an estimate based on our understanding of when we think we're going to see thermal breakthrough as a result of simulation. We will run that circulation test until we do see that thermal breakthrough. We're trying to get to about 2 degrees C, but what we're really looking for is a flatlining, essentially, of the rate of change in the temperature. And depending on that observation of thermal breakthrough, we'll have some different well placement options in 16C. I think we've eliminated one of those placements largely, and I'll talk about that in the next slide. We're trying to achieve expected commercial operation uptime of about 95%. So everything we're doing in preparation, in getting the testing commissioned, and developing our circulation testing is really focused on maintaining a constant commercial rate so that we model as closely as possible what operators will be doing. The two potential placement options for the 16C well, which is the well we'll drill either later this year or early in next year. The first option is that we would drill between 16A and 16B, but offset to the north with a greater distance of about 600 feet at the heel and a shorter distance at the toe. That's partially to evaluate a different well configuration um, to look at the impact of heel bias and see if there's a well configuration that could mitigate that impact. The other option would be to drill essentially a monitoring well directly between 16A and 16B in the connected flow paths. That contingency is there in case we don't see thermal breakthrough during our circulation test. That being said, I think we've decided that it makes more sense to just continue circulating until we see thermal breakthrough. One reason is that um, we could go in and we could drill this well directly between 16A and B, and then a week later see thermal breakthrough, and then we will have drilled a very expensive monitoring well. That being said, it would be interesting, similar to HFTS and HFTS2, and the pilot that ConocoPhillips did in Eagleford to drill through fractured a rock and see what it looks like at some distance from your wells. The 16C well is going to be instrumented. We will have fiber optic cable installed, as I mentioned, with help from Shell. And then we plan to stimulate 16A and 16B, the rest of 16A and 16B first with 16C as an observation well. And then we plan to stimulate 16C. We will circulate for some longer duration, have the potential for power generation. The 16C well at this time is likely looking to be a production well. And we hope to be able to install an ESP in the 16C, partially because we hypothesize that that would actually reduce the amount of water loss if we're able to do that. And it might help us balance our parasitic losses as well. We also plan to drill a well of opportunity, and that is a well that will be used for testing for various research and development projects that the Forge project has funded. All right, so to summarize the impact of the Utah Forge project, Utah is now the global epicenter of enhanced geothermal systems, research, development, and now commercialization. Utah Forge developed and tested foundational technologies that de-risked investment in enhanced geothermal systems. And I think you can see that with how successful Fervo's IPO has been recently, that there's a lot of enthusiasm and now a lot of confidence that enhanced geothermal systems can be commercial and profitable. Utah Forge directly infused Beaver County specifically economy with over $660,000 from 2024 to present. And then significant additional investments are ongoing through 2028. That area has experienced quite the infusion of activity from commercial activities as well. K through 12 education has benefited from over 100 Utah Forge team school visits in rural communities and tons more in urban areas as well. But it's wonderful to see the amount of engagement and the enthusiasm for the engagement within mostly sixth grade is the target audience, and seeing kids learn about geothermal and become very enthusiastic about it is really a great outcome for our team. And as I mentioned earlier, over 133 terabytes of free data released to the public for research and commercial use, significantly more terabytes coming as a result of the ongoing activities. And with that, I'd like to thank you for your time and attention, and happy to answer additional questions where I can. And as I mentioned earlier, if you have any requests for specific data or papers talking about interpretation of some of that data, feel free to reach out. We're very happy to help you find what you're looking for. All right. Follow up on the question above. The heat content would be different for a system that is water saturated versus CO2 saturated. Has this been quantified in model simulations, or was it assumed the system is water saturated? Can I ask a clarifying question? I don't know if you can unmute, or just feel free to type. Uh, do you mean for the natural system or the EGS system?
Yeah, hi. Yes, so obviously for the natural system, which is outside the stimulated part, right? But I guess if you produce the heat transport ultimately would reach into that as well. So I don't really know. That's why I'm asking if it has been factored into the simulation, or was it just simply assumed at that time when this was done that the system is water saturated, right?
Right.
This would have to be redone with the new understanding that is originally a CO2 dominated system.
Yes, no, that has not yet been incorporated into simulation. That being said, there's so low permeability inherent in the system that we're not, we don't think that that's going to impact sort of the native state simulation. And because we're injecting so much water in the enhanced geothermal system, we don't, other than the chemical impacts, we don't think we're going to see thermal transfer impacts of the CO2 phase.
Well, but even if it is in the single percent range, it may not be mobile, the water, right? But and since you have a fluid inclusion background, right, I don't have to remind you, that there's obviously a pore fluid even in the tightest rock systems, right? And
Oh
it
yeah,
can be low, right? But
absolutely.
given that the heat conductivity and is so much higher in the water compared to rock, right? Small percentage of that could have an impact. I don't know. That's why I'm asking if it
Yeah,
has been
no,
calculated.
it's definitely worth investigating, and we're going to be continuing our simulation efforts throughout the project, evaluating sort of impacts as you mentioned of some of these fluids. But another sort of knock-on topic to what you're mentioning is that we are very interested, sort of from a research perspective, in what CO2 as a working fluid would look like in enhanced geothermal systems as well. Research into that has gone back decades, but I think there's evaluation of CO2 as a working fluid again, both from a subsurface and a surface perspective. So it would definitely be a topic worth investigating, I think. So thank you for raising it.
Thanks.
Yeah, also good to see you. Okay, so, oh, thank you, Sid. Do we know if the neighbor next door has used proppant? Yes, absolutely, they have used proppant. And in the forge testing, where proppant was not used, we were not able to establish nearly as much connectivity. And so I should have mentioned that stages 1, 2, 3 did not have proppant initially. Proppant was used during the refrac, but the connectivity was significantly more with the proppant than it was without the proppant. And we also think you need to do a small frac in the producer to establish the connectivity you're looking for at commercial rates. So small frac, a little bit of proppant in the producer, and we had pretty good connectivity as a result. Right now, we were using quartz proppant. I am not 100% sure what they're using next door, but I'm pretty sure it was also quartz proppant, at least initially. I know there's a lot of high strength, high temperature proppants that are being developed commercially out there for geothermal applications. And I think I've talked to some other companies out there who are very interested in using those proppants.
Hi, Kristie. Great talk. I have a question about tracers. I'm interested how you guys use the tracers. Did you look just to see, like, in the past, what we've seen is like it's either you see yes, no, it's contributing or it's not. Is that how you use them, or did you use them further? And then be really interested any papers you have about like tracers or fiber to see that.
Yes, yeah, I'll definitely be happy to send you some of the work that's been done on tracers. Chris Fred, who worked with the Resman team, did some significant amount of work to interpret the tracer results. And then I would say that the yes no is of course very useful, and there are some caveats with chemical tracers. A lot of them have to do with the sampling that you're doing and making sure you have good sampling coverage, because you may very well miss significant concentrations of tracers coming back in certain instances. We really need to follow up, I think, in future work on integrating the tracer data into simulation more robustly, because a low concentration could mean a couple different things, but it might mean that you have a significant amount of flow diluting out those tracers. And so oftentimes low concentration is misinterpreted as poor connectivity, or just inefficient fractures. But in fact, your most efficient fractures might have the smallest concentration of tracers, depending on how much fluid is diluting it out.
Well, thank you.
Yep. But yeah, I'll send you the papers and the work done to date. That's definitely an area I personally am interested in following up on a bit more. I like to look at mass recovered as a metric. So mass injected versus mass recovered. Of course, that requires some interpolation between data points. As I mentioned, you may have missed something significant in between sampling events. But I think mass recovered is a good indicator. And looking at the shape of that mass recovery, as far as was it really early that it was mostly recovered and then it trailed off, or is it a consistent recovery over time? I think that data can tell you a lot about subsurface behavior, and is often overlooked from a cursory evaluation of tracer recovery.
Yeah.
These are great questions. Really appreciate it. Any other thoughts or questions?
I guess I have a second question if nobody else is gonna go. For your fiber work, have you been able to utilize that fiber long term, or was it more just in the beginning of the project? Like, we've been told the amount of data you get can be really hard to get fiber data over months or years, but it can be really valuable when you're looking at your thermal breakthrough temperatures.
So the initial fiber that was installed in 16B, some of the fiber did not last. The one that did last lasted about a year, and we were able to get a pretty significant quality and quantity of data. That was the one that was like Shell partnered to help with that installation, and we are hoping to have that again with 16C. Right now, we have fiber optic sensing in coiled tubing in 16B, and that hopefully will last through our circulation testing. So far, so good. We're still getting data. So, and it's been installed for a little less than a year, maybe about 9 months.
Okay, that's promising.
Yes, yes. And of course, as part of this project, we're very interested in seeing opportunities for disposable fiber and other dip-in options. So hoping to do continued testing of the fiber optic sensing, not just testing with fiber optic sensing as a data measurement.
Definitely.
Yeah, and if anyone has any suggestions for that or any additional interest in, helping frame that up, feel free to reach out, and we're always connecting and talking to people who have great ideas and great opportunities to test tools, equipment, various things. So yeah, any additional questions?
Kristie, I just wanted to let you and everyone know that this is recorded, so I will post this in a few days once the recording becomes available. And so if anyone missed it or needs to rewatch it, they'll have access to that.
Yeah, that's a great reminder.
Well, if there's no other questions, is it okay if we just wrap up?
Yeah, absolutely. Really appreciate your time, attention, questions. Definitely feel free to follow up and ask additional questions. Always happy to point you to data, share what's happening. If your company would like a presentation, just let me know. Happy to have additional conversations afterward, anytime.
Okay, well, thank you everyone for joining us today, and thank you, Kristie, for that great presentation.
Yeah,
Thank
thank you,
you.
everyone.
Okay, thanks all. Bye-bye.